Welcome to Olympiad Math for Year 4. This is Lesson 19, we'll learn planning and optimization strategies. In this lesson, we will learn the principle of coordinated planning and optimization, then coordinated planning in problems involving maximum and minimum values. No matter what task is at hand, efficiency and effectiveness are essential, that is, accomplishing more with less human effort, materials, money, and time. This involves coordinated planning issues. For example, how to transport goods from one place to another by the shortest route or with the lowest shipping cost, how to choose the shortest path from point A to point B, how to arrange and coordinate one or more tasks to minimize the total duration and maximize efficiency, and so on. Solving these problems requires the mathematical idea of optimization, striving for the best outcome while saving as much effort, resources, and time as possible. In this lesson, we will learn about these concepts and how to apply them effectively. Example 1, as shown in the diagram, there are 4 residential buildings A, B, C, and D along a street. A mailbox is to be installed. To minimize the total walking distance from all 4 buildings to the mailbox, where should the mailbox be placed among the 4 buildings? If the mailbox is placed at point P between buildings A and B, as shown in diagram 1, then the total walking distance from all buildings to point P is AP plus BP plus CP plus DP equals AD plus BC plus 2BP. If the mailbox is placed at point P' between buildings B and C, as shown in diagram 2, then the total walking distance becomes AP' plus BP' plus CP' plus DP' equals AD plus BC. If the mailbox is placed at point P' between buildings C and D, as shown in diagram 3, then the total walking distance becomes AP double prime plus BP double prime plus CP double prime plus DP double prime equals AD plus BC plus 2CP double prime. From the 3 cases above, we can see that placing the mailbox anywhere between buildings B and C will yield the shortest total distance. Some maximum-minimum problems can be visualized with diagrams. By listing out various scenarios and comparing them, we can identify the optimal solution. Example 2, there is a cube-shaped gift box, as shown in the diagram. A ribbon is to be used to connect 2 of its vertices, A and C'. How should the ribbon be arranged to make its total length as short as possible? We can unfold the surface of the cube into a flat layout, as shown in the diagram on the right. This transforms the 3D spatial problem into a 2D plane problem. Since the shortest distance between 2 points on a plane is a straight line, we connect A and C' on the unfolded surface. The line passes through the midpoint M of segment DD'. Therefore, on the actual cube, we locate the midpoint M of edge DD', and connect C' to M, and then M to A with the ribbon. This path gives the shortest length of ribbon from A to C'. We often use the fact that the shortest distance between 2 points is a straight line to solve shortest path problems. For example, in diagram 1, to travel from point A to point B, one may go through C or through E, but both paths are longer than the direct segment AB. Hence, in triangle ABC, AC plus CB is greater than AB. As shown in diagram 2, any other way of connecting A and C' uses more ribbon than the path C' to M to A. For instance, connecting C' to D, then D to A, or connecting C' to G, then G to A, both paths are longer. This is because the sum of any 2 sides of a triangle is greater than the third side. Example 3, the diagram on the right shows a tourist map of a scenic area. Point A is the bus station, and B, C, D, E, F are 5 tourist spots. Li starts from A, visits all 5 tourist spots, and returns to A. What is the shortest possible distance he can travel? The numbers on the map represent the distances of each road segment in kilometers. To start from A, visit all 5 tourist spots, and return to A, Li should avoid repeating roads whenever possible. Whenever there are multiple path options, he should choose the route with the shortest distance. By examining the map, we can see that the shortest route is, start from A, go 4 km to F, then 3 km to D, 3 km to C, 3 km to B, 5 km to E, and finally 4 km back to A. Thus, the total shortest distance is 22 km. Example 4. Along a highway, there is a warehouse every 100 km, as shown in the diagram. There are 4 warehouses in total. The numbers shown in the diagram represent the amount of goods stored at each warehouse in tons. Now, the goods are to be consolidated and stored at one warehouse. If the cost of transporting 1 ton of goods for 1 kilometer is $1, to which warehouse should the goods be moved in order to minimize the total transportation cost? We can calculate the transportation cost for each of the 4 possible destinations, warehouses A, B, C, and D, then compare the results to determine which option has the lowest cost. Cost of moving all goods to warehouse A is $10,000. Cost of moving all goods to warehouse B is $5,000. Cost of moving all goods to warehouse C is $6,000. Cost of moving all goods to warehouse D is $11,000. From these calculations, we can see that moving all the goods to warehouse B results in the lowest total transportation cost. The answer is the lowest transportation cost is achieved by moving all goods to warehouse B. Example 5. There are 5 villages located along a road extending from the county town, as shown in the diagram below. The numbers marked on the segments represent distances in kilometers. Water pipelines are to be laid from the county town to supply tap water to each village. 2 types of pipes can be used, thick pipes and thin pipes. Thick pipes can supply water to all villages. Thin pipes can only supply water to a single village. The cost of laying thick pipe is $8,000 per kilometer, and thin pipe is $2,000 per kilometer. By appropriately combining thick and thin pipes and connecting them efficiently, the total cost can be reduced. What is the most cost-effective plan, and how much would it cost? Label the 5 villages from left to right as A1, A2, A3, A4, A5. Since thick pipe costs 4 times as much as thin pipe, it is more economical to use thick pipe when the same pipe supplies 4 or more villages. For 3 or fewer villages, thin pipes are more economical. Thus, it is cost-effective to use thick pipe from the county town to A2, and use thin pipes for the remaining villages farther down. Here is the breakdown. Between A4 and A5, use 1 thin pipe, it costs $4,000. Compared to thick pipe, this saves $12,000. Between A3 and A4, use 2 thin pipes, it costs $16,000. Savings compared to thick pipe is $16,000. Between A2 and A3, use 3 thin pipes, it costs $12,000. Savings compared to thick pipe is $4,000. Between A1 and A2, using 4 thin pipes costs the same as using 1 thick pipe. But from the county town to A1, using 5 thin pipes is more expensive than 1 thick pipe. So, from the county town to A2, lay 1 thick pipe, covering 30 plus 5 equals 35 kilometers, it costs $280,000. Total cost using this most economical plan is $312,000. Example 6. A person departs from Campbelltown and plans to visit Wollongong, Liverpool, Parramatta, and Newcastle each once, finally returning to Campbelltown. The travel costs between each pair of cities are shown in the table below. Can you help design a route that minimizes the total cost? Use 5 points to represent the 5 cities, Campbelltown, Liverpool, Wollongong, Parramatta, and Newcastle, and connect each pair with the corresponding travel cost, as shown in Graph 1, based on the original diagram. From Graph 1, we can see that traveling directly from Campbelltown to Newcastle or Parramatta is expensive. Replacing these with routes like Campbelltown to Liverpool then to Newcastle suggests we can eliminate the direct Campbelltown to Newcastle and Campbelltown to Parramatta routes from consideration. Therefore we can get Graph 2. Campbelltown must connect to Liverpool and Wollongong to enter and exit the circuit. That leaves 4 simplified optimal routes to compare. Let's now break down the remaining routes one by one and calculate the total cost for each. 1. Campbelltown, Liverpool, Newcastle, Parramatta, Wollongong, Campbelltown. Cost is $130. 2. Campbelltown, Liverpool, Parramatta, Newcastle, Wollongong, Campbelltown. Cost is $135. 3. Campbelltown, Wollongong, Parramatta, Newcastle, Liverpool, Campbelltown. Cost is $130. 4. Campbelltown, Wollongong, Newcastle, Parramatta, Liverpool, Campbelltown. Cost is $135. Therefore, the 2 lowest cost routes are routes number 1 and 3, Campbelltown, Liverpool, Newcastle, Parramatta, Wollongong, Campbelltown, and Campbelltown, Wollongong, Parramatta, Newcastle, Liverpool, Campbelltown. Each route costs $130. In this problem, we begin by eliminating the expensive routes, an approach that reflects the principle of keeping the best and removing the less optimal. The previous examples focus on how to consider multiple factors in an organized way to seek the most efficient solution. This is often achieved by comparing different options, using the given conditions to rule out unfavorable cases, and gradually arriving at the optimal plan. Here are the practice problems for today. Thank you for watching and hope you enjoy your math today.